In this example, I'm trying to determine whether or not this series converges. So I said investigate the convergence. We're going to try to either show that it converges or show that it diverges. And just some preliminary work here, I can see immediately that it at least passes the divergence test. In other words, the terms have a size approaching 0 as n goes to infinity. Now remember, the divergence test can't tell us that a series converges. It's just a quick and dirty way of showing that a series diverges if its terms are not going to 0 as they should. I investigated a little bit more by using a computer to get some of the partial sums as n started to become large. If you add the first 1,000 terms of this series, you get 7.5. If you add the first 10,000 terms of the series, you get 9.8. If you add the first 100,000 terms of the series, you get 12.1. So it's growing rather slowly, but it doesn't seem to be hitting any kind of ceiling and settling down to a particular number. So I'm going to say like this, it looks like it might diverge. And that means if we continue this process and take the first million or billion or trillion terms, the sum is just going to keep growing and growing. The way to get a handle on this one is by comparison to the continuous function 1 over x. And I'm going to bring that into the picture real quick. So in yellow, I'm showing the curve f of x equals 1 over x. And of course, f of 1 is going to give us the first term of this series. F of 2 would give us the second term. That'd be a 1/2, and so on. So f of 1 is 1. F of 2 is a 1/2. F of 3. So the areas of these shaded rectangles are actually giving me the terms of the series that I'm interested in. Each of them has a width of 1. So the first one has a width of 1 and a height of f of 1, or 1, and that gives me the first area in the series. The second one has a height of f of 2, which is 1/2, and a width of 1. So that's the second term of the series. The third one, a width of 1, a height of f of 3, or 1/3, and so on and so on. So when I suspect that a series diverges, I set things up this way to show that the sum of the series is an area bigger than the area bounded by this curve. And then what I'm hoping to show is that the area bounded by the curve, in other words, the integral, is infinite, and therefore the sum of the series would be infinite as well. First, let me write that we figured out the sum of our series, that is, the areas of all of these red rectangles, is actually bigger than the integral from 1 to infinity of our function f of x. Then I can actually compute the integral of the function. So that's natural log x from 1 to infinity. When I take the natural log of infinity, I get infinity. The natural log of 1 is 0 for what it's worth. So I just showed the sum of the series is bigger than an area that's infinite, therefore it diverges.